Modern automobiles operate as highly connected software-defined vehicles, or SDVs. These machines navigate using sensor fusion and make decisions through deep neural networks. They rely on constant bidirectional communication with cloud infrastructure to process data in real time. Legacy vehicle architectures functioned as a collection of isolated electronic control units, where a brake module only communicated with the brakes. Because SDVs link all these components into a unified cyber-physical system, a system failure now extends beyond simple broken wires or localized software bugs. A perfectly coded, mechanically flawless system, operating exactly as designed, can still cause a fatal crash if it is targeted by an adversarial hacker, or if its neural network encounters a weather pattern it was never trained to recognize. Evaluating an SDV using the isolated checklists of a traditional car leaves massive blind spots. True reliability requires a framework that assesses internal logic, external threats, and environmental variables simultaneously. This matrix maps the 4 domains required to cover the modern risk landscape. The first 2 pillars are ISO26262, handling deterministic functional safety, and ISO21434, governing defense against cybersecurity threats. The final 2 pillars address external and cognitive limits. ISO21448, SOTIF, manages sensor limits, while ISO8800 tests for non-deterministic AI data bias and uncertainty. Engineering a vehicle to pass all 4 of these standards simultaneously is more than a matter of fulfilling 4 separate lists of requirements. These standards frequently demand contradictory behaviors from the vehicle's architecture. What satisfies functional safety can create digital vulnerability. Reconciling these 4 standards requires engineers to manage technical requirements that frequently oppose one another at the architectural level. The core mandate of ISO 26262 functional safety is to prioritize human life. If an anomaly occurs, the system's baseline response is to open access and release energy, a philosophy known as fail-safe. ISO 21434 Cybersecurity operates on a different logic. Its mandate is to protect core assets and data from hackers. When it detects an anomaly, its default response is to lock down access and quarantine the system, a philosophy known as fail-secure. We see this clash in the door lock module. At highway speeds, a severe power loss occurs. Functional safety interprets this as a crash, commanding doors to unlock. Simultaneously, cybersecurity interprets this as a hacker breach, commanding doors to lock. Strict, isolated compliance to both independent standards results in a paralyzed system, trapping passengers inside a dangerous physical environment while defending against a digital threat. Attackers understand these conflicting mandates and use a technique called error shadowing to weaponize the vehicle's own safety standards against it. In a flooding attack, a hacker simply blasts the internal network with meaningless traffic. The safety processor's watchdog timer detects the latency, assumes a catastrophic malfunction, and forcefully reboots the system, deactivating autonomous steering at highway speeds. To prevent this, assessment teams must verify that engineers have abandoned binary shutdown protocols. They implement fail-operational architectures. Instead of fully shutting down, the system shifts to redundant hardware and alternative communication channels, maintaining a degraded mode that allows the car to safely pull over. Engineers integrate parameters like alive counters and freshness values into the data packets. This gives the architecture the mathematical context needed to distinguish a physically broken wire from an active flooding attack. The architecture must be designed to cross-examine its own errors. Survival depends on contextual intelligence, not just adherence to a single standard. Beyond opposing philosophies, engineers must navigate the strict limitations of computational resources and physical time. This timeline tracks the fault-tolerant time interval, or FTTI. For high-risk components, an emergency braking command must be processed and physically actuated within milliseconds of an obstacle being detected. To satisfy cybersecurity requirements, this braking command must be wrapped in cryptographic protocols like SecOps. This highly optimized cryptography consumes 4.3 milliseconds of that budget. Furthermore, encryption bloats a standard 64-byte data packet by up to 28%, creating severe bandwidth bottlenecks. Engineers resolve this resource clash by offloading security tasks entirely. They deploy dedicated hardware security modules or use cherry-based memory architectures, processing the cryptography on separate physical hardware to bypass the main processor's workload. Over-securing a vehicle digitally without expanding its processing hardware can physically crash the car by forcing it to miss its real-world braking window. If the safety department analyzes physical hazards and the IT department analyzes cyber threats in separate silos, these architectural conflicts are certain to reach production. Modern systems engineering forces the integration of these models at the concept phase, using co-analysis frameworks known as HARA, SAHARA, or chassis. Separate hazard and threat analysis tables merge into a unified risk matrix. Here, digital attack seizability maps directly against the physical exposure rate, and digital security impact intersects with physical severity, generating a singular, mathematically precise risk score for the system. To streamline the production pipeline, there is industry demand for a super assessor, a single auditor certified to evaluate all 4 ISO standards at once. This diagram maps the 4 distinct foundational sciences of the standards: deterministic logic, adversarial cryptography, systems environments, and probabilistic data science. Functional safety relies on predictable statistics, tracking the mathematical decay of physical hardware. Cybersecurity relies on active exploitation, defending against hackers. AI safety introduces yet another foundation, relying on the interpretation of massive, non-deterministic data biases that completely defy traditional rule-based software coding. Forcing one human mind to deeply evaluate all of these contradictory scientific paradigms simultaneously reduces complex engineering to a superficial box-checking exercise. The only valid assessment model is an integrated multidisciplinary team. Experts from each distinct field are governed by a cross-domain lead auditor, utilizing model-based systems engineering to track the ripple effects across the entire architecture. Software-defined vehicles evolve through continual AI and software updates throughout their operational life. ISO 8800 and 21434 mandate post-production DevSecOps and MLOps. This requires assessment teams to constantly monitor the vehicle's real-world telemetry and over-the-air updates. Every time an update deploys to the fleet, the delicate architectural balance between functional safety, cybersecurity, and AI certainty must be re-verified in real time. Autonomous safety requires a continuous, living argument, defended every second the vehicle is on the road.